la transmisión. I've been told that this is okay. I can use both doors, but I don't know. Okay, let's start. I think I'm not missing anything else. If there's any technical issue that is missing, you tell me, please. I hope sound is okay. Otherwise, just tell me. The other day, oops, I don't know. The other day, the microphone was not working well at some point, and nobody was mentioning. Okay. Hello, everyone. Welcome. But by the way, is anyone here who was not last week at the camp, like just arrived or anything? Okay, I expected that. Okay, so you all already know how this works. In case you don't know me, my name is Agustin Gutierrez. I will be lecturing the whole second week of the camp. So today we will have the first lecture with me. This is the work final groups, right? Okay, so a bit of how we can organize it in general. Put it more like this. The sound is okay if I put it more like this, right? Or not? It's too loud? Okay, maybe far away. That's nice. Okay, let's try this. First day for technical tests. Okay, better? Okay, good. It's still too loud, I guess we can ask the volume somewhere to be put down, lowered. Let's hope this is okay. Okay, good. So, again, so now we have a bit more people. Okay. We'll start with the presentation. I am Agustin Gutierrez. This is my second favorite Monkey Island t-shirt, very important. There will be a pattern. Okay, so you've already gone through the whole week with Andrew. We've had awesome lectures with Andrew. Unfortunately, Andrew already covered what I think are the most important topics, so now I will have to fill with unimportant topics. I hope you like them anyway. I do my best. I hope we have some fun. So about the contest, also another difference we had, like the trademark Andrew super system last week. We are not having the trademark Andrew super system. This week we will be using the judge, basically. Have you all used the judge before, or who hasn't ever used the judge? Actually, everybody has used the judge. Oh, wow. Surprise. Okay, we will be using VJudge. Actually, we have like 6 different online judges of sources of problems, so that's what we need to. It's very convenient for me to use VJudge for merging. I think Spock, however is it pronounced, like a spearman judge, is might be especially, let's say, problematic regarding. Actually, Spock works fine, and it's like the combination of VJudge and that stops working and then restarts and so on. If it happens to not be working and there are Spock problems, then we just send you the links and we will use them. The CSS, the super increíble system de enviar a Spock, and that is basically that you send directly to Spock the problem and also to the VJudge, so that when it restarts, the scoreboard is nice. This is what we do. I think all the other judges work, but if they don't, you will use the same system. Okay. It's good that you will use the VJudge before, so there's very little to explain. It's like a judge that combines other judges, a meta judge in that sense. Okay, and I think you all received the link that we will be using to the group already, so if any of that at any point doesn't work, you just tell me. So, okay, awesome. It should be easy then, hopefully. Okay. Is user Shoots 1927 here by any chance? Oh, he's okay. If you think the contests are too hard, you can blame him because he was the main person who asked for the contest to be extremely hard this week. No, I'm just joking. I just prepared them the way I was going to prepare them anyway. Regarding defect, but he did ask for hard contest. That part. Regarding difficulty and topics of the contest, they are not specifically thematic, so again, they will be like a mix, not like if today I speak about one algorithm, then today there shouldn't be 10 problems about that algorithm, right? You might notice that there might be a few more sometimes that have to do with the topics I have explained, but so slightly thematic maybe, but not fully thematic. Okay, you will see that they cover many different topics. Okay, and also about difficulty, I think Andrew's contests were explicitly increasing in difficulty, and he said so that was to be expected. These ones are random surprise. So, right. So the theory is that way you can practice not knowing and being prepared for everything, right? You have to be prepared for an easier contest and for an extremely harder contest, right? Because otherwise, if you only practice one of those, your strategy gets completely messed up if for some reason, like, your next contest is much harder than usual or vice versa. And also, about the topics, they all should be varied, but there might be a few contests might be more focused on something. And the same for how many problems and such. Everything is random. What else do I want to mention? Oh, okay. Please ask questions to me at any point. That is quite important. Also at coffee break, right, we will follow the same structure of, I don't know, like 115 minutes of class or something like that, then coffee break for 20 minutes or something like that, and then ask for the rest approximately, right? So any question you have also during the contest, I will be here, and don't hesitate to ask questions if you want. You're probably working on the content very hard, but from problems of past contest and such, if you want any topic that wasn't clear, or you thought, or if you had afterthoughts after the class, feel free to talk to me in either Spanish, Portuguese, English. I don't recommend Russian. You can try. So that's another thing. Okay. Yeah, I had a super perfect slides prepared, but I saw that Andrew's a great teacher and he was using only the Blackboard, so I thought, oh, this is better, and I threw them away. So no. I might use one day, but today this is. Okay, I think that's all for like preliminaries, right? And a short introduction. I hope I like the middle of any questions that anybody wants to ask? Okay, good. Right. Most people have arrived already now, so let's start. Okay, so what we'll be talking about today? Actually, another pattern with the lectures that I will be giving is that I think that, well, some of them will have a very clear topic, but they might be a little more, let's say, mixed than past week we had a very well-defined topic, and some will be like a mix of maybe a few different things. If I will say that to put a title on today's lesson, we could just give it a very generic title. So let's say today we will be covering data structures and graphs. Well, things about data structures and things about graphs. So very generic. Okay. Okay. So just to give like an index, we will be covering a few, I would say binary structures, but there might be a few, I don't know, different things. So some data structures and interesting things we will cover. That is like the first part. And then I expect to cover a few things on graphs today, basically. Maybe we do a short recap because I hope you know very well already, like EFS, like things like strongly connected and such, right? So that we get, I want to mention a trick which I don't know how to call, but let's call it fast DFS. You likely know about that. This is the kind of thing that, okay, where do I fit it? I just mentioned it, right? And then like the complicated algorithm, the main topic that you might know or you might not know, the graph arborescence. This is not a hard word, arborescence. Algorithm. By the way, who knows? Who has heard before about what is an arborescence in a graph, which is like a spanning tree but with directions? Explain it very badly and very quickly. Who has heard about it before and who knows how to solve it? Like polynomial time. Only polynomial time. For now, it's enough. Oh, okay, and a few were raising hands. They might know what it is and not how to solve it, I guess. Okay, so nobody would know how to solve it in polynomial time. Okay, good. Then we hope to learn that today. This is not very common, but like I mentioned, like the most important things I think were covered, so we can get to more unusual topics. Okay. Okay, let's go. So regarding what missing any name, I mentioned as many different tricks or data structure that we might mention, we might talk about. We basically divided like in three parts. I don't know, let's say in general, counters as an introduction, a few observations on binary counters, ternary counters, and their complexity. Very simple. Actually, before all of that, I will just recap about the standard, very basic binary heap, which you might not use often, but you should know. Then again, lacking a better name, let's say we talk about binary composition or decomposition. I don't know, it depends on how you think about it, right? And then mail-double heaps. Has anybody heard or implemented any kind of mail-double heaps here? Good, great. Does anybody know about Fibonacci heaps or heard about Fibonacci heaps? Okay. Those would be an example, but we will not use Fibonacci heaps today. You can forget it. Has anybody heard of binomial heaps? Oh, they are less famous than Fibonacci. That's surprising. Those we will mention, and they are easier than Fibonacci heaps. So that's okay. Okay. So First of all, just a quick recap on the basic binary heap data structure, right? This one is like very famously covered in algorithms and data structures courses, right? And if you start competitive programming on a language other than C++ and very old like Pascal, which is not used too much now, you might need and decode this algorithm a lot, but it's not a meta right now. So what is a binary heap, right? Who knows what a binary heap is? Like, I guess most of you. Okay, but some are not raising their hands. Just we'll do a quick recap. So conceptually, it's a binary tree, right, with the same structure as a segment tree, basically, but the nodes have a totally different meaning. In a sense, in the standard binary heap, we can have max heaps or min heaps, right? I tend to prefer to think of min heaps where we are interested in the minimum of the time, which is, for example, what Dijkstra or Prim algorithm like, because we want low costs. But the standard C++ priority queue is a binary heap, but it's a max heap, so that's why you usually have to reverse it. So let's fix min heaps. For a min heap, basically, for those that happen to know segment tree more than heaps, a heap has the same structure as a full, complete, very nice binary tree. There might be missing nodes if the size is not exactly a power of 2, and the usual way to handle it in the case of the binary heap is to just fill in like this row major order, right, as we read, basically. So you keep adding nodes, which is the natural order when you number them. I think Andrew numbered things from 0, so I will do from 1 just to be different. Okay, but it's obviously the same. We use the same trick, right? We actually store it in an array, which is very efficient, very nice, very convenient, and that way actually new elements are pushed back, right, on the vector, let's say, or the array or whatever. And if we have to remove elements, we know that we will have to remove from the back, and perhaps move things around to respect the invariant. So basically, we almost know what a heap is. The invariant that we have is that we will store things in the nodes, right? The elements themselves will be in the nodes, and like the sec tree that has them in the leaves, let's say. So in that sense, it's more similar to a binary search tree, another structure that we mentioned before. So I don't know, for example, we might have values 7, 8, 8. Binary heaps usually allow repeated values without any problem, unlike set, for example, in C++, that you have to be very careful, right? So something like this. And the invariant is very simple. It's for every node, its parent has to be lower than the node, right? Because it's a min heap. For a max heap, it's the other way. That's the only thing. So it's like very loosely sorted. It's like I started sorting the array and I got bored and I went playing video games, right? And so it's a bit sorted, but not fully sorted. That is a heap. Okay? So because of this invariant, and since the structure is like a tree, the good thing is that the minimum element is obviously always at the root, because we can compare and we have paths from everything to the root if we actually draw this as arrows, perhaps. Each arrow points to an element lower than or equal, so obviously the root is the main element. Okay? I guess most of you already know this, right? So this is very clear. We are now on a common footing. We might mention some other heaps today, which might have interesting properties that I okay, any questions regarding binary heap? Okay. If you happen to not know this but use it, this is the implementation that C++ actually uses for priority queuing, right? So that's why priority queue has logarithmic operations. By the way, I have not explained how to do the operations in logarithm time, but if you know them, great, and if you don't, they are simple exercise. They are basically always add the element and start moving things so that the invariant holds, basically. Just as an example, if I changed any node, if you only insert or delete as in C++, it's even simpler because you move only things here in the root or here. But I could do it anywhere. Like if this one is like 15, I can say, oh, this is too big, so it's now broken. So I will swap it with, okay, it's a better idea to swap with 8, which is smaller, right? So that the smallest one is closer to the top. So I swap them, and now I know that this one is broken, and I keep sinking the node if it is heavy, or floating the node if it is light. That is basically the algorithm, and that's why it's algorithm 10. Okay, this was a recap on binary heaps. This is an awful presentation if this was the first time you saw binary heaps ever in your life, but I guess most of you have seen binary heaps. Any question? Okay, this might now be slightly like out of context, but we will have other heaps just in a moment, so it's good to have a common footing. And in general, like there might be other heaps that I'm not aware of, but like there are many variations of more advanced heaps, like a few that we will mention. And in general, like all the heaps have this structure that they are a tree, or many trees sometimes, but they have trees, and the invariant is the same. This is like the heap invariant for all the heap variations. The heap invariant, which is the most important part, is when forming heaps, the parent of any node is lower than and equal than the element, right? And other heaps will relax this very tight, I am a binary tree structure, or I am a full binary tree structure, or whatever. They will start losing what kind of tree switch will happen. But they will still keep that invariant. Okay, good. Okay. So let's talk about data structures now, more the data structures. Some of these, and possibly most of these tricks or data structure that I will mention next, will be amortized time, right? I will mention it so that you keep it in mind. And so as Andrew mentioned in one of the classes last week, most of these are not convenient if you have to like roll back or keep adding and removing elements. That many of the tricks we will see now work very nicely because we only add the things and never remove. But I will mention specifically that the last ones will actually not be. Okay. So speaking of amortized, let's speak about amortized counters, which is a simple idea that you might have encountered before, especially in amortized analysis classes at university. So I will basically set it up with a problem. Let's say you have an array, right? And this algorithm will take like exponential age of the universe time, but we don't care. We're thinking here only. Okay, this is theoretical example. Because otherwise you would use integers and it would be very fun. So let's imagine you have n digits, right? Binary digits, but let's pretend it doesn't fit in an int, right? Or something like that. We can only use an actual array of zeros and ones. Okay. For example, n is 1,000, and we can run this for many ages of the universe. Okay. So I want to implement a binary counter. So just with an actual array of zeros and ones. Perhaps it is convenient for my implementation. It probably won't be because bit masks are so convenient and easy to check the bits, but let's follow the idea because it can be useful inside variations of this. So I actually want to count up to, well, let's say we have t digits. Let's say I want to count up to n. So if I do it in place, I will just, again, have to add 1 to this element, then I will have to add 1 to this element, and so on. I trust that you are able to implement this plus 1 logic, right? You basically add 1 to the end and do like the school addition algorithm, but with only 1. So you just have to check if you overflow and carry 1 and keep going. Okay? So my question is, what is the complexity of well, setting up the arrays order D that's already there. You have the zeros already there. What is the complexity of using this counter and doing the plus ones? I mean, let's say just doing the plus ones to get the final value. If you count up to n, okay, n might be, I don't know, a million. What is the complexity? Anyone?
If you do that algorithm.
It is order n log n for sure. Like, it is very easy to bound it like this. Yes, a number up to n only requires up to logarithm of n digits. So if we go from the n backwards, checking the plus one, if, like, if it ends in 4 ones and a 0, I know, okay, it has a 1, it has a 1, it has a 1, and I do this. This will take up to a number of digits, and I do that n times. So this bound certainly holds, right? To n, okay, I only care about the general term here, but yeah, it might be something like 2n. There might be actually this might be an amortized constant operation, right? And this is true, it's nice to know, right? It's not so common to use a binary counter like this exactly, but there are some algorithms like that work in this way or have something analogous to the binary counter. It's good to, it's convenient to know that this actually has linear complexity, right? And the proof is relatively simple. Let's just imagine that this were a clock, right, that ticks every second, like, okay, 1, 2, 3, 4, and like that, right? It ticks everything. If we look at the bits one by one, we will see that this one flips every second, right? So every second, this one flips. But the second bit, the second most significant, least significant bit, sorry, this one, if we keep going, would flip, this would be a 1. This one would flip less often, right? This one would flip basically, if we check the pattern, every 2 seconds, right? So it's clear that each digit flips like twice, has a period of flipping events twice as long as the previous one. So from our n operations, we might say simply that, okay, about, well, all of them have to use this last digit, but only about half of them have to use this digit, and only about a quarter of them have to use this digit, and so on, right? And if you do this sum up to infinity, well, you have 1 plus a half plus a quarter plus an 8, which I hope you, this is the informal notation, but this is, if you cut it anywhere, it doesn't reach 2, right? This is like, I mean, a cake and say, okay, this is 1, this is a half, this is a quarter, this is, okay, you can clearly see that you're reaching twice the original cake, right? This, I hope you know that this holds for any multiplicative factor lower than 1, right? This is geometric progression. Okay, so good. This is actually a nice thing to know, basically. Okay, so this is an example of an amortized counter, basically. Okay, it's nice to know that there is no extra logarithmic factor to worry about, right? Doing this, if I actually need a counter that will count up to n, will have amortized constant time, right? The total time to count up to n is per thread. Okay, is that clear? Okay. It's good to, it's worth noting that the actual time of the operations of each plus 1, let's say, in the worst case, can be logarithmic, right? Of course, at some point, I will have like a number which has many ones, and I will be forced to do a lot of work, right? Like the logarithm work. So there will be operations that pay the logarithm factor, but if we analyze, it's infrequent enough that the total is order n. So per operation, the average cost is order 1. Okay. So now I have a question for you. Is this specific to the binary counter? Or, I mean, if this was a decimal counter, I could do a similar. If these were digits of a number. I see many of you doing like this, so I will assume that you see the pattern that this generalizes to counter in any base B, right? Any base B, we can do the same. And for bases that do not happen to be power of 2, in some brute force problems, especially, we might have to try all the combinations of something that has states like there is a button, but instead of press and not press, it's like pressed, not pressed, and half pressed. So you have to try the 3x3 combination. That can sometimes be inconvenient to do. But it's good to know that if you implement a quite simple actual array of numbers with zeros, 1 and 2, and do the brute force with a while, the extra while averages out, and it has a worse constant factor probably, but it's like using bit masks, right? But they will be ternary masks, right, or whatever, explicit, yeah, the same for base team. It's actually more efficient for bigger bases because it becomes extremely infrequent to go to larger values. Okay. Okay. Any question? Oh. So there are two more little examples I want to mention related to this, which are just slight variations, but they are worth mentioning so that you know. Sometimes, especially in encoding problems or things like that, it might be useful to think in terms of something that you can probably invent yourself. It is more or less natural if you have this kind of, I need to encode permutations or something like that things. But there is something actually called factorial base. Have you heard of this? It is the idea of having a number encoded, but the base, like for a binary number, we use digits 0 and 1. For a decimal, we use digits from 0 to 9. For a ternary number, we use digits 0, 1, 2. Right? Well, in factorial base, that is not fixed. So we just use a crazy rule. There are slight variations of this idea. But the most straightforward, I think, would be, okay, the first digit has one possibility. And for the second digit, from the least significant, right, up to the most significant, we can always imagine that all numbers are infinite and have zeros on the left, right? That's a very usual way to think mathematically about numbers. And so on. So each digit has one more option than the previous one. So in base factorial, the last digit will always be a 0. So many definitions might actually just drop this and say, okay, that doesn't make sense, let's start from 2, right? So for the last digit, it is either a 0 or a 1. But for the next one, it is either a 0, a 1, or a 2. And for the next one, it's either a 0, a 1, a 2, or a 3. Okay, and so on. Have you seen something like this in progress, like you needed to use this? I mean, just imagine counting with this, right? So how would a counter look like in factorial base? Where is all zeros, like the first elements, so this would be like number 0, and then here I am writing in decimal, right? Yeah. If I want to count in base decimal, how would this update? Okay, +1 to the last element. Then I would have to do +1, but it will go out of range, so it will loop to 0 and add 1 to the next, exactly as we always do with numbers, right? But in base factorial, it is somewhat crazy that the last digit is like a binary digit. It flips back and forth, but the second digit has 3 values, 0, 1, and 2, and so on. This is actually 4, and this is 6. Okay. Okay. This is in many problems involving permutations and counting. I need the if permutation or something like that. it's very convenient to reason in this way, like being able to move from your number to the explicit writing in what is called factorial base, right? Because this decomposition is like telling you, if you think about a combinatorial problem, this structure is like it maps the number of combinations for the first 8 digits is like the factorial, right? Because you go multiply. So this, especially if you add like the last final fixed 0, right? For example, for 4 digits, it would be like, okay, I have 4 values to choose from. Which one have you chosen? 0, 1, 2, or 3, right? And for the second one, I have 3 options, 0, 1, or 2, right? They are like normalized to 0 and to 2, but any process where you have like a permutation or things like each step you have less options, if you have like to code a construction of like like from this representation build a solution, it is usually much more convenient to have like the base factorial representation and not the actual number, which it is harder to read the digits that way, okay? But the numbers are usually more convenient for encoding, and I don't know if you have to do BFS or something like that on these values, you would like to maybe put them all in a map or something, and then having actual numbers is more convenient, at least if all of this is small enough, so the factorial combinations can be still helping. Is it clear what I mean by this? Have you used this kind of idea in progress before? A few people have, but not many. Okay. It's not like ultra common, but it does appear. So it's good to notice that this works like other bases, right? In what ways it works like other bases? If you actually have a number and want to decompose it in base factorial, you can use the usual algorithm of start dividing from the back and getting the digits from the end to the beginning. You just have to change that algorithm so that the number by which you divide and take modulo keeps growing, right? Because you have more possibilities. You could do it from the left to the right too, but the calculation is not as easy, so more convenient usually to do it. And the final thing I wanted to mention, some problems or some processes actually keep doing steps in such a way that they, for example, generate permutations or something, in a way that maps the process so they have like the same complexity, the same way of working as actually doing a counter in base factorial, right? It would be like, okay, I do +1, but if it overflows, I go back to 0 and add 1 to the left, and if it overflows, and so on, but with thresholds that are increasing like this, right? So I hope you see by this point that if you have any such problem, it will actually like amortize to order n, right? I mean, if you have to count from 0 up to n in base factorial, it still is amortized n, and for the same reasons, basically. I mean, the calculation is a harder number, but it is even smaller than in the binary case. So it is easy to still be order n. Any questions? Okay. Regarding this way of reasoning, right? Who can give me an example of an algorithm that we usually don't implement ourselves? It's already there. That will be a hint. That has a way of working and a complexity that will precisely match the complexity and the way of working of the counter in base factorial, right? And those we can say by this reasoning, oh, okay, actually doing the count that way, even though it might not look order n, is order. I mean, if we count up to, I don't know, usually it is factorial, the number up to which we count, let's call it t. If we count up to t, it will have complexity order t. Yes, next permutation. Next permutation, if you started, it should be the sorted permutation if you started for the amortized analysis, otherwise you might have one extra n factor at the beginning, because if you give it the completely inverse permutation, the first step completely reverses and restarts, right? But yes, using next permutation, which by the way, you should know how it works and how to implement yourself, right? You should not be lazy, you should think about the standard algorithms and how you would code them if you did not have them, right? Not to do it, but to know how to do it if you have to tweak or do a similar idea. So next permutation is like a greedy algorithm. What it actually does is construct the next permutation from the given one, and it just goes from the right until it sees something that is that can be swapped to increase the lexicographic operation. And here it is basically, okay, 5 and 6 can be swapped, so the next one would be 6, 5, right? If I call it again with this new value, it will say, okay, 5, 6, it is growing to the left, so I cannot swap anything. It is already as large as possible. I need more number. Oh, 4, this one is smaller, so I can't swap. And which one will it swap it to? Well, the smallest possible value that is larger than this, so that it is actually the next lexicographic. So in this case, it will be 5. But it will always be this last one, because in this case, we are already growing the number, right? So it's like the swaps that it does are fairly deterministic. So they don't depend too much on the values. And yes, if we pay attention, the actual permutation, the base factorial encoding, and the number, which would be just the ID. This is the 0th permutation, this is the 1st permutation, this is the second permutation. Like they are all encodings of permutations, actually. But it is interesting that how much next permutation takes every step is the same as how much the simple factorial base counter takes every step, right? And that is why it is actually constant amortized time. Right? Okay. Any question? What? Okay, so now we would be pretty warmed up about thinking in amortized terms. So we're prepared to see a more advanced version of a fairly similar idea, which I don't know how to name, but I have named it binary decomposition or composition, right? It depends a bit on how do you think. But at the core, we will go back to this binary counting or bits idea, right? We won't have bits, actual bits in our algorithm, in most implementations at least, but we might use them for somewhat advanced problems. I have actually a motivating example of powerful things, which are quite unusual, but powerful things we might be able to do in a relatively simple way with this idea, so just as motivation. We have, I think, the apocorasic algorithm has been mentioned last week, I am pretty sure. So of course, now you can go with your eyes closed. This is super easy. Otherwise, you have it in your notebook and you can copy paste it. So apocorasic receives patterns and a text, right? Or actually, we will have a pattern. That's pattern and text, basically, right? So the usual way it works is that you receive many patterns, you pre-process them, create that triangle, the magical structure, which is the apocorasic automaton, basically, and then you're ready to receive as many texts as the user wants, and you will be able to report matches very efficiently, right? But what happens if a new pattern arrives? well, I actually don't know how to do it incrementally in any very meaningful way. I don't really remember if there was a way to do it, but I would have to think a lot, and perhaps it is like impossible to do it in a very efficient way. But we might have a situation where we, in an online fashion, receive patterns and texts, right? We cannot have all the patterns at the beginning, we cannot have even all the text at the beginning, and we have to be prepared for, okay, a new pattern, well, and they update us with new patterns all the time, and we always have to be ready to, okay, now I have this text, match, okay? And of course, the complete naive way to do it, but not fully naive, let's say, using a heuristic would be to rebuild the automaton from scratch every single time a new pattern arrives. Right? That would be the logical way, which would have, let's simplify it to quadratic random, right? Because let's say in the length of the patterns are strings. Because if we are alternating pattern query text, right? Pattern text, we would be rebuilding the automaton every time, which is linear in the pattern, so it adds quadratic. Okay. So it is interesting that we can find like a general idea, which is an interesting idea on how to compose that data structure that you might have seen before. You certainly have seen, I guess, similar ideas, but maybe not exactly this version. Which, if I am not super mistaken, should be able to handle this because it's very generic and it works with many algorithms that can just build a structure with all the data as a black box, and they don't care how they use it. So this is like motivation problem, perhaps. So how can we use what we have and try to think on an idea on how to improve this, maybe, and do anything at all better than building from scratch? Well, there is an idea which we might call binary composition, which is, okay, if I have, the core of the idea is to essentially use powers of 2, because powers of 2 always help in computer science, always theory, right? That would be like the core idea if I had to say, okay, how to remember this. But let's think about it a little more. Like in this case, where we receive one pattern first, then we will receive another pattern, I don't know. We have elements or things that are added into our structure. In this case, it will be patterns. It is natural to think that the patterns are added because the texts are like queries here. We not modify the setting for future queries, right? So here the data is the patterns, right? So we can imagine that we have, we might, for this setup that I mentioned, for everything to work nicely, we might want that all the patterns have the same asymptotic length or something like that. But I think it should not worry, be a problem, but let's not worry about that. This is just a motivation. So we will have at any point n data points, let's say, that have been inserted. Here, the most natural thing would be that the patterns of the data point, but it could be something else. So what do? We write n in base 2, so that we decompose it in 2 powers of 2. So if we have 6 elements, we can think of 6 as 4 plus 2, right? If we have 9 elements, we can think of 9 as 8 plus 1. If we have 7 elements, we can think of 7 as 4 plus 2 plus 1. And what does it mean? Well, it means that we can actually, if we want, store this structure into, let's say, substructures, right, of sizes power of 2, right? If I have a structure which has received 6 data points, okay, it will actually be decomposed in my implementation into one substructure with 4 data points and one substructure with 2 data points, right? If at any point I have a structure of 9 data points, okay, to me it will have to be decomposed into 8 data points and 1 data point, 2 substructures, let's say. So we are either decomposing the big structure into the smaller ones, or we can think that we always are composing, which the code will actually compose smaller ones to build larger. Okay. So this is the abstract idea, right? Just as an example, I might want to do like a classical textbook example, which is easier, but I wanted to impress you first by showing, okay, we can throw very wide things into it. A more textbook example would be binary search. Okay, binary search is already the solution, but the problem would be just to search, right, for an element in our collection, right? So in the standard setting, we might need to add elements, right, and search for a desired element. Or perhaps something like lower bound, like which is the of the index of an element. We could do all of those things, right, with binary search. And we know of powerful structure that can do this specifically, like the binary search tree, the C++ set. But this framework would allow to keep adding numbers at any time and solve the problem of search. The idea in that more elementary case would be, okay, to solve a searching problem, I would like if the problem were offline and I knew the numbers, like I knew they will send me numbers like this, I will say, okay, I just want to sort this. This is much better. So actually I will sort it first and then do things with the data, right? Well, then my idea would be that each substructure is actually just a sorted array, in that example, for example. Right? So let's say that initially I am given number 7. So then my whole data structure is a single array of size 1 with the number 7. Then I am given the number 2. So my whole data structure is a single array with the number 2. But now I have 2 arrays of the same size. So this is like incorrect in binary, right? This would be like writing the number 0, 0, 0 and a 2 at the end. I have 2 times the bit of value 1, right? So this is like how to know when I need to merge. I want to always have this kind of decomposition. So for a structure of total size 2, it should actually be a single substructure of size 2, not 2 substructures of size 1, right? So essentially I need to merge these 2 right now, right? So when the 2 is added, I notice that they have 2 of the same 2 blocks, let's say 2 substructures. In this case, they are arrays of the same size. I can merge them. So if they are sorted in this particular case, I can actually use a specific algorithm for the merge, right? Which is the merge sort, right? But I could even just join them and sort, and call the sort function, right? This method is still useful many times, even if you rebuild from scratch, right? If you just create a new unordered block very chaotically and call it sort, then you have the new structure. Like, the difference between those two would be a log factor. It's not like the whole idea breaks and we don't create an interesting algorithm. So this is like the idea. That's what I mean by binary decomposition. Instead of having one single structure, the two sides, you can always decompose it into smaller structures of size power 2. This is actually quite similar to what many at least memory managers do with the blocks. They do something like this. This idea is very used in memory management, right? So in implementation-wise, it will be the other way around. When elements are added, I basically create a new structure of size 1. That should be trivial. A single element, a single structure, perfect. If there weren't any, let's say I am going from 6 to 7. Right? If there weren't any structure of size 1, that is perfect. Nothing more to do. Just add. So I will need a list or something of my substructures, right? I can just append, okay, I have a substructure size 1. Perfect, because there weren't any before. If I now go from size 7 to size 8, okay, I would want to create another one of size 1 with a new element, but I need to merge this. So I will do that, they are merged, and I have one of size 2. And if I want to count, I would say I had 1 before, but I have 0 now of size 1. And now I have 2 of size 2, which is wrong. So I will merge them, and I will have 1 of size 4. So if I want to count, I had 1 before, but I have 0 now. Substructures of size 2, and so on. Here I had 1 before, but I will have 0. They will merge, and I will emerge triumphant with a single structure of size 8, right? And if you notice, like, you could, if you imagine that you stored an explicit mask that helped you and told you, like, how many you have of each structure, of each size of substructure, the idea is that if you include all the sizes, like 1, 2, 4, even the ones that don't appear, right? The mask will match the binary writing of the total number of elements. Right? This is more like an idea. Is it clear? Okay. So now my question arises. Well, this is a very abstract setting, right? So depending on each particular problem, we can use it to solve different kind of queries, right? Back to this simpler example of binary search. If these were actually arrays, and I just keep them sorted, so that is my structure. When I have to merge two arrays, I will have two sorted arrays, merge them. The super naive way or the linear time way, but in the end I will have one big sorted array. So, in general, what I have is that any number of elements that have been given to me in an online fashion in any order, at every point, I have them more or less sorted. I exactly have them sorted into different arrays of power of 2 size, each of those sorted. And since they are all different size, there is a logarithmic number of substructures, right? That's very clear at this point, which is one of the nice things of power 2. Right? So, for example, for this searching problem, if I want to solve any of those questions, like the index of the element, which would be like how many are lower than this value x, which is also an online query, right? I didn't have x while building this structure. At any point, at any intermediate point, I can be asked how many elements are lower than x or similar things. Well, they will all reduce to binary searches on each of the components and then combining those results, right? For this kind of queries, the combination will be easy, right? For other queries, it might be impossible, so it depends on. We need to be able to combine, right, results for whatever query we want to do. But as long as we want to do that, we can do that. We can use this very general setting. Like even for a complicated structure such as a Hokorasic, which has a full automaton, for a problem like this, what we could actually do is just like the naive sort idea, like, okay, the merge will just be put them all together and call from scratch the build a Hokorasic of this new thing of twice the size, right? And if we do the calculations, that will already be improving the complexity from the naive for every single pattern to the build the automaton, right? So let's do a bit of that. Let's reason what complexity we have. First of all, is there any questions? And if not, what complexities do you think this building of elements have? Well, it is sort of a trick question because it might depend on the complexity of the merge, right? So let's first of all imagine a happy case, right? and assume that merging is order 1, right? For problems like this, where we would actually have a sorted array, well, this is extremely optimistic. We will not use two ordered arrays into an ordered array in constant time. But anyway, if we think it is constant time, we are at least counting how many merges we have to do. Okay? If the merge is order 1, what is the total cost? So how many merges do we do in total for n elements? Like, if in total we have n elements ever appearing in our world, right? Like the final largest total size is n. In terms of n, what will be the total number of merges, right? So the complexity as if merge was order 1. Like the bare minimum complexity if merge is just constant time. That's a good idea. I like that way of thinking. That's why I was showing the other thing before. You have to be greedy with lessons. Yes, actually, if we look at this carefully, it sort of replicates the binary counter logic, right? But with merging of data structures, right? If we actually imagine those explicit masks of zeros and ones that just tell me, okay, I have, for example, for size 10, I could have a mask that says, okay, I have, let's index them, okay? I have one structure of size 8, 0 structures of size 4, one structure of size 2, 0 structures of size 1. That is the way I can actually decompose 10 into 1, into 8 plus 2. And this one I'm not used to right now. So in terms of the masks, it is actually a +1 because it will always replicate the writing of the number. So the data structure is actually like following the binary counter. If I, just for the sake of reasoning, imagine that I am doing a binary counter in parallel at the same time. The way merges are being done is identical to the carry of the +1 carry, right? When I do the +1 in the binary counter, right? So for the same reason as before, every half step, I put the new element and do nothing, and half of the time I have to do a merge of structures of size 1. So basically, if I count how many merges are size 1 merges that create a size 2, there will be n divided by 2, right? And as in the binary counter, I have to wait for 4 elements to build up so that I get 1, 2, and another 2 to have 2 collections of size 2 in order to merge them, right? So that will happen every n divided by 4 steps, and so on and so on. For the same reason as before, this is total linear time. So very few merges are done actually in total. Only order n. It is even less than we might expect. We might expect n log n, right? So if the merges actually happen to be order 1, the amortized time is extremely fast, right? Of course, we might have other merge costs. For example, in our example, let's put another letter to it, like in terms of the size of the data structure that I am merging. Okay, if those sizes are S, okay, it would be order S to do a merge in this example, for example. This would be a typical representative, like more or less linear time, okay, in the things that I am merging. Actually, for the build from scratch version, this would be S log S, right? I would sort the concatenation by brute force. So, can we now reason what would be like the complexity? The brute bound would be quadratic because I do at most n merges in total, and I multiply by the worst case of this, so n times n squared. But that seems too pessimistic, right? And we give a better bound. Right. That I think that one is correct. Can we think of why this one will actually hold? it might be similar or exactly the same reason as some other well-known algorithm, perhaps. That would be one way I would prove it. Like, oh, I already know this other extremely well-known algorithm, and the proof is the same, right?
In each term of the sum that we had, like for the binary counting, we now have the size as the numerator, so it cancels out and it gives just those times that, because the sum will give low.
Okay, that's right. Yeah. Everybody sees that. That is a good point. If we repeat this calculation that I have here, okay, the last bit is merged. I mean, size 1 is merged n divided by 2 times in total, and that one, if it is linear, that one it goes multiplied by 1. If and then size 2 is merged n divided by 4 half the time, but it is twice as large, so this one is multiplied by 2 for the cost. And if we keep the pattern to the left, each one is half the time, but twice the cost. So they all cost the same, and now, well, we cannot do the infinite summation that would diverge, but still, we know that our actual summation goes up to log n. So it is actually n log n. Right. That is perfect. And that, another way to think about it, which is more combinatorial, but is actually equivalent, as counting the same thing in different way. Linear size means that each element pays for itself, has to pay its cost when it is merged. Like I can imagine, no, I am not paying the cost. No, I don't want to pay. The cost is paid by each element. Each element has to pay me when it is merged, right? That will give the total payment, right? I am not paying it, the elements are paying me, but it is the same. If when I merge, I pay the size of the substructure, I get the same total as if each time something is merged, each individual element, like in structure of 2, each of these 2 things pays me, right? That's what I mean. Then if I count for each element specifically how many times it has to pay me, well, every time it is merged, it goes to something twice the size, right? It moves to the left. So each individual element can pay me a cost at most log n times. So the grand total of payments is at most n log n, right? That is the same exact proof as the, well, I say it is small to large technique, but that is using union finding, right? The simple implementation of union by rank is n log n because of this same reason. Okay? Everybody sees this idea? Did you know this binary decomposition of structures idea? Or okay, many people didn't, some did. Okay, so it's a mix. But it is a nice idea. It is quite unusual, unfortunately, to use it like exactly like this, but the pattern of how to merge and like the kind of ideas involved in this, I think, can appear in problems that have like a similar result. And of course, if you're lucky and you see a problem where this is a perfect match, great, use it. Okay, good. So just as a recap of our initial example, with a very simple sort, arise, merge, so the data structure is trivial, no nodes anywhere. Like arise and vector, basically the data structure, and sort and binary set. With that structure, we would be able to add elements at any time online, and also support queries online at any time of what is the index of this element, right? We cannot delete elements. That is a big limitation of this thing, this general framework. In the general framework, in the general case, we cannot delete things, but we only add. Everything amortizes to a very nice complexity, and we only have to merge. And there is one more thing that sometimes is quite convenient. Many times it doesn't change too much. But by doing it this way, for example, let's compare it to another technique that I already mentioned. This doesn't, I think that this is not so used in competitive programming because we have like a general, powerful, still polylogarithmic something technique that kills everything. What would you say is that general idea? Segment tree is not, although it might in many problems. Like in a more data structure, especially for trees, especially for trees. Right, the fact that we have set is one thing, right? But that is a fair point. But let's imagine that we have to merge things. We cannot easily merge sets. If we had like a problem with a tree, and we are merging things and having to, well, we sometimes need to merge sets, but it will be too slow. But we can fix that by using, I think someone very quietly mentioned it, we can use the small to large idea, right? I'm sure almost all of you has at least once used that idea. But that general pattern of it could be summed up like in a simple general framework. Like I have many, I also have many sub-collections which I am merging at some points, and now they are not fixed to be power of 2, but what I now do is that in small to large, the key idea is every time that I do a merge, I merge the smaller one into the large one, right? So if we are detailed here, in small to large, as long as this linear time is actually linear time in the small one, not the total. If it is linear in the sum, then small to large will potentially be quadratic. But if it is linear in the minimum, let's say, because I take care to merge the small into the large one, that's small to large, then by the same proof, even though there are no powers of 2, each element moves to something twice the size, at least, or more, so it cannot move more than log n times. By the same proof, it will be n log n. So I think this is not used a lot, because small to large is so powerful and so convenient. Right? But if we have a problem where we have something like small to large, where we would normally use small to large, but for some reason it doesn't work well, well, we have this other idea that might work. Like, don't forget this exists and check it. For example, there is one very convenient thing with this general pattern of merging, right? This binary decomposition. Maybe it's the binary part. In general, small to large, we have collections of any size, and we have to merge two collections of any size, right? But here with this idea, we only merge 2 powers of 2 of the same size to the next size, right? We only do merges like of this kind. One size becomes the next one, and they are always power of 2, right? So we have like log n cases, right? So to speak, we could even hard code it. They are small enough that you could imagine them seeing them on a screen, right? Which is impossible for 100,000. So that sometimes might be convenient, like the fact that in some problems you might be able to use that I am merging 2 things of the same size explicitly, right? Not of free size. And even more, it's power of 2. Like it's if I can use that sometimes if it's convenient. Like I can do divide and conquer directly. No need to pad or anything. It's not very common, but that can help, and it will help you when example this in just a moment. Okay, there's one more important thing I should mention about this pattern, and then I think we can go to break if the break is already there. I hope. Can someone check? So we'll mention one more thing, and then we go to coffee break if it is available. So far, we have been focusing on. Let me actually delete this. Erase this. Sorry. We've been focusing so far on adding elements one by one, which is like the easy, let's say, case, or the natural thing to do. But we might have a union find, basically, right? The union find situation, which is also what I was just mentioning as a small to large application situation where we have also DSU, right? These are all different names for very similar things. We might have collections of things. In this general framework, we explicitly do it even if it's not in the problem. But maybe our problem or our setting directly involves collections of free size, perhaps not necessarily power of 2, I guess, but in general any size, that are sometimes like merged. And oh, I need to merge and I have one super big structure, right? Like the reverse of mitosis, basically, something like that. And then I have other structures and I have like online queries or updates of, okay, now you have to fuse these two, right? That is a reasonable common thing to want to do. And for common queries, we sort of know how to do it. Actually, as I was explaining just a moment ago, anytime that we have something like set, which it is true, it was quickly mentioned that it is a very powerful, useful, and convenient structure to already have there. Anytime that we can add elements by one in a reasonable time, like small to large, this idea of insert all of the small one into the large one too. When you have a merge, it's like it transforms a merging problem into a add one by one problem. And it has to pay like an extra cost of logarithmic time. Right? Do you see that? Like the insertion is easy, like a pushback for the union-find basic structure. But by doing small to large, we end up with n log n total time. If this was a more complicated problem with sets, well, the insertion into a set is logarithmic, but still we can have a set per node and do some small to large interesting thing while we compute. And the total time ends up being like n log square of n, right? Like because of this idea that each element is inserted at most logarithmic times, well, the total time is of using small to large is n log n times the cost of a single merge, a single insertion of one element, right? So it is a very nice pattern, small to large, because it transforms the merging thing into the add only one thing, which many times can be done more efficiently. A homorasic would be an example where I am not sure that we can add one string and rebuild like quickly, like not in time proportional to the full automaton. We might be able, but I think we can. You tell me later. It seems hard. I'm not a string expert, actually. Luckily, I'm not speaking of strings. Okay. Well, the thing is, so another reason why this kind of idea, I think, is not used too much in programming context, because it actually is, and most of the time the solution can be done with other things. I think it's typically like small to large. Like the killer to this idea is like most of the time you can more or less get along with small to large. But this is like a different thing, it's a different problem. This idea can be used and is interesting for the merging problem, right? And in many cases, it can do similar things to small to large with one less logarithm, basically, right? Because you can see here that, I mean, we still haven't done the merging, the full merging, right? But we will see just in a second that it will be essentially the same idea, and it will not change complexity. So when merge is constant, instead of n log n, we get n. When merge is, well, here it is linear because I would have to do many insertions, but if I weighted this like per element or per insertion, the cost was less than I pay in log n, and so on. Many times I can get rid, it depends on the detail, but I can get rid of one log compared to small to large. So then, all of that is to prepare my question. How do I use this idea of binary composition to do a problem of merging? So, for example, in this same example where I was using sorted arrays as my sub-collections, and that was my interesting data structure, because my queries were going to be binary search. So when I add an element, I do all that I explained, everything was working. But now I have like many heads, similar to persistent, that I can have like many versions of the structure, but here they are independent, right? I have some elements, so I have one of these superstructures that is built of substructures. My friend has another superstructure that is built of other substructure, and we say, hey, let's merge it all together, right? So two superstructures, we want to super merge them into one big thing. How do we do it, and what will be the complexity? So let's Let's choose one arbitrary example. This might be okay. Let's imagine I had a structure of size 9, so abstract something like this, and my friend has something of size 7. So we'll end up merging those, and we need to arrive at a final merged structure, which happens to be power of 2, but there's absolutely no need for that, right? So here magic happens, and we arrive at the solution. Well, what is magic happens, right? How would we merge two of these things efficiently, right? Let's remember the mask binary idea, because that can help. 9 is 1, 0, 0, 1, right? This expresses one size 8 and one size 1, while 7 is 1, 1, 1, 0, right? And I'm always one away from the solution. Because I have one of size 4, size 2, size 1, okay? So drawing from the analogy of this is all just like counting in binary and numbers that we had for +1, well, this should be like a +7 and the other way around, because the sum is commutative, right? This is like summing everything up. So what will we do for the sum? I will sum and I have 2, 1, 1, 1. Right, I forgot about the carry, right? I cannot have a digit of size 2, I should fix it. So a digit of size 2, like 2 units, is actually the same as 1 unit of the digit to the left, right? And now I have a repetition of 2 of these, and I can so on, so on, so on, right? I can mimic this binary addition with data structures, basically. If I just concatenate this or merge them or whatever, like in one big thing of, then I will have the one of size 8, size 4, size 2, size 1. These one are now mixed, which came from which one, but I really don't care. I won't hold the mix. The thing is, I have 2 copies. I mean, this is now untidy, but this is the way to think of it more orderly, right? Like in columns. I have 2 copies of size 1, so I could actually merge them, so get rid of them and get size 2. And so on. This would mimic exactly every time I have a carry in the addition of the sizes, it represents a merge in the joining of the data structures, and by exactly mimicking this simple binary addition, I will get to the final size with the correct sizes of the substructures. Right? That is the idea. So no really new operation. It merges all the way down. It's always merging, merging, merging. The only thing I have to think is what to merge with which is basically any time I have 2 things of repeated size, I merge them. Right? And by merging all together, one might worry, okay, but this might get out of control because initially you only had 1 repeated substructure, but if you merge 2, let's say you have 2 of size 7, you will merge all of this, and now you have many repetitions, right? But then it helps to think about this as a binary addition, right? In the binary addition simple algorithm, if we merge from small to large, but in a totally different sense from small to large. If we merge from the smallest digit to the largest digit, right, like this, and we do the carry, right, in binary, every single time that we carry, that is a merge, right? So the traditional binary, simple, direct digit by digit binary addition shows us that there won't be many merges. Actually, we don't need more than 1 merge per size at most, right? We just have to go from smallest to largest in the same way as the others, right? So actually, any fusion operation, let's call it let's say this is a fusion, right? When I merge 2 superstructures, let's just call it a fusion or a meld, to distinguish it a little bit from a merge, which is the smaller merge, right? Because now we have fusions with 2 merges inside. So actually, any single fusion of 2 data structures, the big ones, inside only does a logarithmic number of merges, the small ones. That's a nice guarantee to have, like only a guaranteed logarithmic number per operation. But because of the same reason as before, the total number of merges is not actually n log n, which holds from that bound, but it's actually linear time. Because the total number of carries does not depend per digit position, does not depend on how I reach the final size n. If I added it one by one, if I added it in two blocks, giant blocks of 7 and 7, still per position, it's the same as before. Per position, I cannot merge here more than n divided by 2 times, otherwise I would have merged too much, there would have been too many elements to begin with. I cannot merge more than n divided by 4 here, and so on. So by the same sum, once again, the binary counter sum, this is linear time, a linear number of merges in total. Right? So this is the nicest part of this idea, to me. The fact that you can fuse with a guaranteed logarithmic number of merges, and actually the total number of merges is still log n, as if you were adding by one. That is a very nice property. Any questions? Oh, and just as before, if the merges, because the analysis is the same, again, if the merges are linear time in the size, it doesn't matter if in the maximum or the minimum, because this idea only merges things of exactly the same size. So the size is one and only size, right? But at every operation, there is no large and small. The total will be n log n, which I think if you do the analogous thing with sets small to large, it will probably n log square n, which might be easy to get rid of doing any of many things that you can do. But it is nice that this one will only arise that gets a nice complexity immediately. Right? Any questions? Okay. Okay, so this has this nice, usually one log factor less because of nice amortized properties, nice implementation. Well, that is subjective, but at least nice idea. And the fact that you only have to merge things of identical size. You don't have to merge arbitrary size. I think those are the nice properties of this concept, right? This binary composition concept. Many times you skip all of that and do small to large, and it works because it is a very powerful technique, the small to large, but I think it is nice to know this one too. Okay, let's do the coffee break, and then we'll see some related applications and a few graphs. Is the volume okay here, I guess? Yes. Happens to be too loud or anything, you tell me please. Okay, let's mention moldable hips. This seems too long, but this is not used very often like the other thing actually. So let's mention it anyway because it is a very nice idea. I'm slightly surprised that many of you mentioned that you know Fibonacci heaps, but not binomial heap because binomial heaps are much simpler, and I think in courses they are like always taught before. So maybe it's just that Fibonacci is much more famous, which makes sense actually. Actually, like Fibonacci heaps is like the superpower version of this one, but we don't need this at all for today's purposes, right? The main famous thing of the Fibonacci heap is that it was the first one to achieve like linear time for the Dijkstra algorithm, right? Except for the n log n part, but n log n plus m, like linear algebra. If you're interested in those kind of things, actually, as a side note, I very strongly recommend you to read about hollow heaps, which I am pretty sure were published by the same author, Tarjan, like something in the last 15 years or something, instead of 50 years, like the Fibonacci heap. And it's like he published a paper again, like this structure does the same, so it's not new in a sense, but it's much simpler, so it's good. We have a much simpler version that does the same. Okay? So it's interesting. This is like the easy Fibonacci heap, so it's nice to read. But that is just a side note. Today we'll talk about moldable heaps right now as a nice example of a data structure that like combines extremely well with the general pattern that we said just a moment ago. Okay, so as a recap, we have like the problem that we would like to do fusions. Right? Fusion is that we have many elements that at some point we have already built into one big structure, and many of those possibly. So instead of the initial setting where we have only one and only one structure, we might have many different structures and they keep merging and merging, just like yes, right? So merging, those would be actually a fusion. We might call it just to distinguish from the small merge. Okay? So what if we want to have a data structure where we always query for the minimum, right? We can use the heaps, right? Like we know already, binary heap is C++ priority queue, which is like the standard textbook thing for queries of minimum, right? If we only have merges and never deletions, we could simply store the minimum and that's it, but we will have deletions. So for now, don't think about deletions, but for this to make more sense, we will have deletions. Okay. So we might want to do this with heaps, right? This is the structure we want to keep. Before it could be, as examples, we just mentioned two, but the framework was very general. We might have sorted array as our simple data structure and composing many of those. We can build more collections. Another example was the crazy automaton, which I have been told and shown that it actually exists in code forces. So if you search for it, there is a problem that you have to do like this basically with the Jurassic automaton. I was happily surprised because I did not do that on purpose. Like I thought, oh, what is very hard to keep? Oh, for example, Jurassic. Actually, I thought of this while watching the lesson last week, right? And then it happens to be the case that someone else had already beaten me to that idea. Now I cannot set that problem. Okay, anyway. So those are the examples we saw. Perhaps we want to keep heaps, right? So we want to keep heaps and be able to use our data structure, right? So the thing is, we don't have a particularly efficient operation to merge, to fuse, to merge two heaps, right? We know that a heap of size, whatever, 5 would be an array of 5 elements. We know that the first one will be like the smallest one, because that's how heaps work, but we don't know a lot about the rest. Like, we know that we can think of this as, just as we do with segment tree, right? It's actually an array in memory, but we think of it as a tree with a certain structure and so on and so on. Heaps are just the same. So if we have two heaps, which are two arrays completely independent, we don't have any particularly efficient way to merge them, right? I mean, we can actually do it in linear time in the total. There are algorithms for that, but we would like to do something even better. That's also like rebuilding from scratch. It does not use really the fact that we already had a lot of structure because these were heaps, right? For example, because we have already seen that if our merge were much less than linear, for example, if it works constant time, a fusion with our idea of powers of 2 only requires logarithmic numbers of merges. So if merge is very fast, we will only add one logarithmic factor to that merge time, and we will have fusion, like completely free fusion, right, of heaps. That might be the idea behind mail-double heaps. The idea is that, okay, the basic heap only care about add elements and remove the minimum. Actually, that's the only important one for the standard heap. Like, those are the key operations. Add elements and remove the minimum, right? Well, the mail-double heaps add on top of those two operations. Okay, we also care about the fusion. We might have two completely independent heaps, and we want to merge them into a single, right? A single new heap. How do we do that? Well, one very well known implementation is the binomial heap, which is basically the data structure you will invent. I mean, because of time, I will just explain it. But if I had left it as homework, you probably can invent it yourself. If I tell you, you have to invent a data structure to be able to very efficiently, like constant time, no allow for anything. Constant time, you have to be able to merge two heaps, right? Because that is like the key idea of how to construct it. Like, okay, let's keep the general concept that all of these heaps do, which is we use a tree. And it might not be binary, but it will be a tree. And we keep the invariants that parents are smaller than children. That way we know the root is the best option, right? The candidate, the winner. And those taking the minimum and removing is comparatively the easy operation. Okay, so we need to be able, so for example, with only one element, we will have a single node, and this is the element, right? If I have another one of only one element, okay, this is the single node. Since I will need to be able to support in constant time the fusion of two of these, I need to be able to do the fusion of two nodes very fast, constant time. Okay, so I just hang one on the other. That has to be the case. So 5 is smaller, so I will put it in the root. It will be like a base case or something, like the smallest possible. But then, okay, this is the way binomial heap of size 2 looks like. This is the way a binomial heap of size 1 looks like, right? Since I want to be able to merge in constant time, that is my goal, well, I will be very greedy. If I have two binomial heaps of size 2, let's invent 3 and 10. Okay, I want to be able to merge them extremely fast into one of size 4. So I will say that the way to do it is to just hang it as brute force, and that's it. That's all I do. And so that the invariant holds, I will choose the smaller one, and the other one is the one that will be conventional. So in this case, basically I will put this, like here, 5, 7, hang it here. This is the other one of size 2. And this whole thing that is emerging here is the shape, actually. The shape that every single binomial heap of size 4 has. That way, you can see the pattern now. A binomial heap of size 2 to the power of k plus 1 is created by joining in this way, like very directly attached two binomial heaps of size, well, one less. Oops, sorry. Actually, with this shape, with this idea, we can get all the powers of two shapes, right? We can disregard the elements because we just have to check which is the smaller, and that one goes above, and that's all we do. We can now basically take a look at how would a binary heap of size 4 look, sorry, 8 look. So this is the shape we have already discovered. This is the shape of size 4. So if we attach another size 4 here, let me make a copy carefully. These are very delicate. You move them a lot and they explode. So be careful. Okay, like that. This is the shape of the Fibonacci heap. The Fibonacci heap, the binomial heap of size 8. Okay. So they are only powers of 2 size, not binomial coefficients or anything. So why are they called binomial? Some of you might be seeing the pattern if you didn't know this data structure already, but the only reason they are called binomial, this is not used at all in the analysis. It's not very important. Like this is just someone looked at the drawing and said, oh, how nice. The number of nodes per level, you can write them down. Well, this might be useful for the analysis. Okay, for that. What we get that it is not too deep, but this will be one way to mention. The number of nodes per level is actually the binomial coefficients. Right? That is always the case. And we know that the binomial coefficients for a certain n add up to 2 to the power of n. So that makes sense. We are only creating things size power of 2, and per level we empirically are getting something that adds up to power of 2. Okay, it matches. So our conjecture makes sense. It is actually true, and that is why they are called binomial. Because per level, it ends up having a number that is the binomial coefficient. And it's, you can see it easily if you think like, okay, I had the array for the previous one. This one would be 1, 2, 1, right? I have the binomial coefficients, and this one is hung before, so it's like shifting the array, and then adding all together. And that is the Pascal triangle formula. That is literally that implemented all together with trees. Okay, so it is. But that is convenient, but not necessary. All we need is that the depth is logarithmic, and that is pretty clear because we increase the size by twice, while the depth clearly goes by 1 more. Right? No need to count the binomials anywhere, but that's why they are called like this. Okay, so is the structure clear? Okay, but this will only allow us to create things of size power of 2. That is a big limitation. We want heaps of any size. What do you think the binomial heap does? For solving that problem. As a tip, we have had a small lecture about this just a while ago. We just have a list of these nice trees. If this is like one binomial heap tree, okay, a proper full binomial heap is just a collection of 1 or more, or 0 or more if it is empty, binomial heap trees, let's say, right? So if the total number of elements was actually not 8, but I don't know, 12, I would have one of these of size 8 and one of these of size 4. So I would probably have like a vector of pointers to the roots, right? Something like that. All of these can be made persistent. We won't talk about that today, we don't need it, but these are all like 3 arrows structures and you can make them persistent on the way. There's no moment when we need to do complicated things that will break persistence at all. Not even add a logarithmic factor to the complexity. Okay, so this is the idea, right? And we can use the pattern that we had before. If an element is added, well, actually, this is an idea shared by the next implementation too. The easiest way to think is just to think in terms of fusion. Okay, just as before, if I have one binomial heap made of many of these, nice trees, right? And I have another one, for example, it could be of size, I don't know, 28, so it would be like this, right? I could do the merge as before and arrive, so I would merge two of these, get one of 16 and merge them, and after the dust settles, I would get the final structure, which has a size 36, which is the addition, if everything was correct there. Right? So this is the main nice things of the binomial heap. We can actually merge very quickly. What is the complexity of the merge? Using this structure. I mean the fusion, sorry. The fusing of two heaps, each of which requires merging some trees. Of a single one. I think for the total, I think that's correct. But for a single operation, right, it is guaranteed, so no amortization. That's a great property. Let's put this in not factorial, this is a surprise. It's order n log n, worst case, not amortized, and worst case. Because we do logarithmic merges, and in this particular, this heap is built to be able to merge in constant time extremely easily. It was built that way, right? So it is logarithmic time guaranteed. So that is the main huge advantage of this. It's very easy to reason, and everything is log time guaranteed. And all the operations will be logarithmic time, even deletions. That is nice. So this one supports. It is based on the idea that might be problematic in general for deletions, but this one also supports deletion without any big problem, right? Basically, for addition, what we need to do is to create a new heap, which is a single heap of a single node, and merge it to the previous. We implement the merge, we already have the plus one. And for deletions, well, actually, you can find in logarithmic time the minimum, because now you have many independent trees, but they are only a logarithmic number, so you check the root one and take the minimum. And if you have to delete the minimum, well, you delete it in that tree, and now it will not be a binary tree anymore, it has many children, right? But again, it has a logarithmic time of children, the root, because you add plus one to the degree of the root each time you build one more. So you end up, just by taking the children, you end up with a correct binary, binomial heap for one less size, right? That stems from observing that inductively all the time every subtree is a binomial heap, and they have they correct all different powers of two sizes, right? So for deleting an element, you can just delete one on the tree that creates a new collection. In this case, for example, we end up with trees of size 1, 2, 4, okay? But that is a new heap that we can, again, fuse with the original, right? We take the tree with the minimum, we remove it, we have this new collection, but they are only logarithmic numbers, and we fuse it with the original, right? The nice operation that does all the work is the fusing with using the previous idea. And it is log n guaranteed time, so that propagates to the other operation. So this one has addition, fusion, removals, all in logarithmic time. The interesting part compared to the binary heap, the traditional binary heap, is the fusing. So I think it is a quite nice idea. Any questions? I recently learned, I mean, this one is very nice. It's very book algorithm, let's say. The theory is beautiful, it works, it is logarithmic time, like guaranteed, no random, so it is actually very nice. And I don't think it's particularly hard. However, there is a randomized bendable heap algorithm, which is also interesting. So I will mention it. I learned about this one very recently. I knew that the classic one was the classic one is the binomial heap. The randomized bendable heap does the same with expected logarithmic time complexity, right? As you would expect from this kind of random algorithm. And it is even more direct or more simple. The whole idea is, okay, the randomized measurable heap will be a single binary tree. Okay, in that sense, it is more similar to a binary search tree. In the structure, it is a binary search tree. Sorry, it is a binary tree, and it is a single tree with all of the elements, right? One element per node. But it doesn't keep the complicated binary search tree invariant. It keeps the much easier invariant of being a heap, right? Each node is lower than or equal than all its children, right? For a mean heap. So how do we do that? And basically we will randomize the shape. That is the idea. And that is enough. So to create a new tree, we create a node as the root with a new element, put the value, and that's it. That is, of course, our base case, right? So let's do the fusion first. Because, again, in this algorithm, like in the previous one, we can actually think of this with a generic tree drawing, right? And these are binary trees. I could just say A, B, C. Right? Let's say this one is lower, right? So if I want to fuse two of these, I actually know which will be the root, right, of the new fused tree. Because the heap invariant has that nice property that the root is the minimum, it is determined. So I just choose which of the two the minimum. Here it is this one, otherwise this one. And that will be the root of the result. So I basically put this one as the root of the result. Right? I am doing the fusion. But the randomized measurable heap, even more than the binomial heap, just implements all of the other things through the MED. Like the MED operation, the fusion operation is the atomic one. That's the main one. So I put this one as the root. I have cut the tree. So now I have this one, C and D, right? This is the situation, but I want a binary tree, right? So what should we do? You want to put this and to have children, right? Sorry, my bad. We're not cutting this one. That is what is confusing. We're not cutting that tree. Sorry. So we know that this one will be the root. So let's just do it over. Okay. Since this one will be the root, okay, this is pretty good. We have to put things onto this one because this one is already the root. So we can do it recursively, right? We can basically either put all of these three merge here with C, and that will be the new left child, or we merge it over there, right? So we either do, let's call this one left, right? Yeah. We either do mel LC, and that will be the new left child, or we do like only one of these, right? Mel L with D, right? And that will create a new randomized double heap, and we put it over there as the right child. And the other child we do not touch it. We only change one of the children basically, and do recursively another method, right? This would be the code of meld left right. This is left, this is right. So it's recursively and very simple, but we have a free choice. Well, instead of always choosing the same one, which will lead to a skewed tree, this is where we do a coin flip. And that is the randomized one. And that's it. Basically, due to this coin flip, the shape of the tree ends up being random, and that is enough to get logarithmic depth. It will enable all the logarithmic context. So this is a very nice idea. I really liked it when I learned that. And this one supports, again, all of the operations in logarithmic time, because fusion or meld is our atomic one, but then if we have to add a single element, like before, we create another, just meld that whole thing. And to remove one, well, we know that it is the root, and then we are left with two heaps of the children, we meld them. right? That will fix everything. And we again get one root. And I think that's it. Yes, those are the elements. You can even implement like the other usual decrease key and such textbook operations, but those can be done also in terms of this. So those are the fundamentals. So this one might be even easier than the other one, I guess. It is quite a nice idea. I like learning about this. Makes sense because if you want to, binomial heaps are like from the year 77, I think, something like that, and this one are 1990 something. So it took 20 years for someone to say, oh, let's randomize this. Makes sense. But it is very nice. And as a final observation, we could do all of this with binary heap or even set, like to put more bazooka power into this, like something like that, plus small to large. We could probably handle even the deletions, right? With both binary heaps or sets, we could do extract minimum operation, and we can see that the complexity still holds because it will be smaller than what it would have been if we had never deleted, because things are smaller, more or less intuitively. You can check that complexity will still work, but it has like an extra load, right, compared to any of these two. So it's interesting, I think. Okay, any question? Did you know this randomized methodology? Have anybody seen this? Oh, what? It's not well known. It should be more well known. This is a very nice. That's right. The binomial heap might not be famous in competitive programming, but it's like academia famous, right? It's the textbook one. But this one I had never heard about, and it's very nice. Yes.
I have a question. It's more about the mindset of solving problems with randomized algorithms.
Okay.
How do you think about when you can use them and when you can't? And when you have like sparse, maybe states, maybe it could be suitable. How do you think of these problems?
That's a hard question. This is a bit case by case, actually. But usually, like to see if a randomized algorithm will help, you have to think like as if you were writing an adversary, right? That can see what, like transforming the problem into interactive is a way to. That would be a way to at least quickly get an intuition, because sometimes you can think of a very obvious like strategy of how to break your ideas. Let's say instead of coin flipping, this could be like a game between two players, right? And there could be like an interaction, and it's like, okay, you can modify the data or adjust details depending on the results of my coin flip. So you can see what choices I do. Choose depending on the result of the coin flip, you can adjust the data. Well, if there is some pattern like, okay, there are a lot of possible things I can choose to make this complexity very bad. That's like an intuition that randomized is not helping. But in many problems, it's like, okay, unless they, for example, the Quixter one, it's like, okay, if you always choose something very close to the border, it becomes quadratic. But because of the same geometric series that we saw before, like anything like a fraction, that's a very fundamental, typical concept. Like when you reduce by a fraction of the input, it becomes very fast. We are using it here with halving. In some programs, it is clear, like, okay, a random choice, no matter what the input is, the input has to be extremely specific, right, so that the random choice is not in the middle, right? So that's an intuition that, okay, random is helpful. But other than that, like general pattern of thinking how many choices of the random could generate like bad behavior. Because I don't know, for example, let's say a randomized algorithm is like
I want to do linear search, so I will speed up an array that is not sorted. So I will speed up. I will speed it up by randomly sampling until I hit the end, right? And in that case, it's very explicit. You can calculate the probability and everything. Like, oh, okay, but the random choice has only 1 in n chance of working. So it's like it's not improving from the right. But not only because we do the full calculations, like on a general sense, like still it's not like proportional to a fraction. It's like once you have to hit like the one correct choice, that will not happen. Here it's like, okay, on average, for things like this which have sizes, it's more like a matter of knowing properties. For example, for trees, it is quite well known that if you insert into a binary tree in random order, the structure is the same as if you do a random permutation, and it's quite equivalent to quicksort, the calculation. This one, I think it's again the same calculation, but like in reverse order, but I'm not completely sure. I will have to think. But it really does look similar to that. So I think here there is that intuition that if you choose randomly, like at each step, again, it's similar to the union by rank. In order for the complexity to be worse, you have to be skewing it to the heavy side. So you do have like 1/2 chance of doing the right thing, right, at each step. And that might be an intuition that, okay, it's not like you have to have one lucky guess among n. You have 1/2 of chance, right? And the complexity increases by 1 if you miss, not like the algorithm fails. Okay. I think those are like the general ideas. But other than that, you might have to do like calculation of if it is enough probability or not. Sometimes for some random algorithm like this, you might experiment, and it can sometimes be done, like to run a simulation and see, oh, okay, on average it is doing few queries, so it works, right? When it somehow does not depend on the data, you many times can do that. Here it slightly depends on the data, but only because of the rules, right? Which one we choose. Any other question? Okay, I think that's all I have about the data structure part. Right, so let's talk about a few graph things. And due to time, I will possibly have to move a few short tricks to tomorrow's lecture, which I think is no problem. I prefer to talk about arborescence today. Right? The other ones are like little tricks to mention here and there. I'm likely moving them to. So, arborescence. What is an arborescence in a graph? Who knows what a spanning tree in a graph is? Great. That's what I was expecting. Who knows what a minimum spanning tree in a graph is? Great. Again, what I was expecting. This one might be. Who knows the Prim's algorithm? Right? Prim. P-R-E-I-M. Okay, a few less. Who knows Kruskal algorithm? Okay, yeah, Kruskal is nicer. That's good. I like it. You should know both. And by name, they are too famous to learn. Okay. Yes, for minimum spanning tree, I think the two most algorithms like far are Kruskal's algorithm and Prim's algorithm. Okay. Prim is like a Dijkstra with a bug, and you introduce a bug into your Dijkstra. You put maximum where you were supposed to put a sum, and then you save the day by saying, no, it was minimum spanning tree, of course. Kruskal is totally different algorithm, which has some very nice properties because it is basically a specific case of matrix. That is why it's has very nice properties. This one is more like it somehow magically works, but doesn't have very nice properties. If you try to, it's easy to conjecture. Oh, this is producing incrementally the smallest tree. No, all of those conjectures are false. It magically in the end has the minimum spanning tree, but all the intermediate things are very hard to study what property they have. Like crosscut at every step has the minimum spanning force of that number of components. Very nice, very clear structure. That is most people who do theory or problems like crosscut. Okay, I think. Okay, so we are not dealing with a minimum spanning tree now. We will be dealing with an arborescence. I think it's written like this. This is actually, let's see. This might be like American versus British, maybe. Arborescence, arborescence. It's a very confusing name. But it's almost like a minimum spanning tree, but in the directed case. You might have thought about this at some point, even if you never learned the algorithm or you do not study, because it might make sense. If we have any like directed tree, right? We could think of, okay, I want a spanning tree, let's say, but directed. And what would be the analogous? Well, the most obvious one is ignore the directions and take a minimum spanning tree, but that is not interesting. Right? A very interesting analogous is an arborescence. And it is basically to choose some node as a root. So from there we already have a difference. The root might be important in these algorithms. And for minimum spanning tree, you can basically choose anyone as the root. And then usually you of course have two versions, because you could say, okay, this has to be a directed tree, and thus all arrows will go away from the root like this. And the idea is that this has to be a spanning directed tree, which is called an arborescence. This spanning directed tree now, with everything directing correctly from the root, away from the root, so it wouldn't work if I tried to use this one. No, I would need this one, the one that goes to the node, if I want to use that. Well, I want to get an arborescence, if it exists, and from all of them, one with the minimum total cost, right? If the edges have cost, I want the minimum total cost. And of course, you can draw the arrows the other way, and it will be like this, right? Going to the parent, right? You often have to think about both things at the same time, right? This is the parent relation, this is the child relation. Depending on which part you are of your code, you might prefer to imagine the arrows one way or the other. But of course, the important thing is that it is consistent, right? I think usually, most of the time, the directed tree itself is represented like this. So we would have, even though we might use the parents a lot in our implementations, this would be the canonical drawing, and we say, okay, we take the parent of this node. So this is the problem we would like to solve, right? I think only one or two people said that they knew how to solve these polynomial terms. Okay, that's nice. It's not very well known. So my first question is, we can use this very well-known algorithm and call it a day. So why don't they work? Or how would we try to adapt them? Right? Because it is very natural to try to adapt them. Just as a recap, for Prim's algorithm, we would start from a node, and really, actually, Prim does, if you run the code, it will create a directed tree, because it's like Dijkstra, right? So it's basically what would be the minimum path tree that Dijkstra builds when you run Prim. In an undirected case, it correctly builds something that is a minimum spanning tree. So it will build, if it exists, some arborescence from the roots that you choose. Let's say that the root is given to us. That will be actually two versions of the problem, which I think both have some of the similar details. Whether it is fixed or you can choose. But for now, imagine it is fixed, so it's like Prim. We start from the root. And we really at each step say, okay, from all of the possible ways to add the correct
to add an edge to the current adolescence, right? So any of these nodes over this to increase. I would like to use like the minimum, right? Well, this one is the directed case phase. Okay, it might be intuitive because the proof was very special. So if you never did directed,
Right. But just as a general idea, both algorithms, part of the reason why both algorithms breaks and this one is harder, I will leave as an exercise to think examples and reason, is that there is a like a nice structure property of the minimum spanning tree that this problem does not have at all, and that might be an intuition of why this one is harder and we need to be more careful. For the standard problem, if you have some graph and compute, I mean, for the minimum spanning tree problem, in undirected case, if you have a graph and compute the tree, the minimum spanning tree, actually. And then you say, oh, I forgot, there were 3 more edges that you had to add, I don't know, whatever. You add more edges, right? Then you don't have to start from scratch. You can add those edges like here. You did not lose important information. It's like the minimum spanning tree has enough. It is very small compared to the original graph. This one is order m plus m if we have n nodes and m edges, while this one is order n. Typically for big M this is smaller. So the minimum spanning tree has reduced the information a lot, but it's still enough. All the important things are there. If new edges for removals, it is not. But if new things, edges arrive, I don't need to start from scratch. I mean, everything that the minimum spanning tree dropped, you can prove that you don't need, right? If new edges arrive. So that's quite useful and can be used in some interesting, like incremental problems where a few edges appear. But this property fails in the directed case. Like if you take an arborescence and remove the rest, and then new edges appear, suddenly those edges that you had deleted were important and become useful. And the intuition might be, okay, you can have things like this, and it's like, okay, any of these will do. I will choose the smaller one. Well, no need to, can be positive or negative, doesn't matter. I will choose the smaller one, I discard the other one, but then I put things the other way, and it suddenly becomes very important that you connect the other way and you forgot what you put. That is the quick intuition, right? And that breaks like both algorithms, because both have this general shape of, oh, I get connected, and I only keep information of what is connected and not the details, right? Losing the details here, you cannot do. That is the intuition. Okay, so this will not work. It's important to have some sense of why it won't work. So now we are we are lost with our nice algorithms do not work. We don't know what to do. So any guess? Let's just do some fun guessing it. Any guess of what? Thinking that, okay, these two did not work, but the problem seems at least similar to the classical, like if all the edges were both ways, it would be the classical problem, basically. It would not have changed. So which kind of algorithms were these two? Like what algorithmic technique did they use? Some people said greedy, and yes, that is correct. These were greedy algorithms. So my very loosely intuitive idea would be, maybe we can do a more complicated greedy, but still has greedy elements, right? It doesn't suddenly become very well dynamic programming. And it sort of works like that. Yeah, we can still do some greedy things. With this idea in mind, one might be motivated to try, okay, I will do some greedy algorithm. And actually, what we will do now, I think, I don't remember all the details, but I think it actually is what the Borufka algorithm for minimum spanning tree does as its first step. Then we do totally different things, but we will do the first same step, I think. So some intuition from the original steps, which is that we might say, okay, what is an arborescence, right? There are many ways to describe it. I use the drawing one, but actually one useful way to think about is always in terms of parents. So we can speak of the parents of a certain node, and it will be, okay,
the parent, right? Which node has, from which node the arrow that arrives at this node lives, right? So if this one is X, this one is X, right? And the root would be the only one without a parent, right? Or a special parent or whatever we do, right? Or sometimes it's the only loop, right? But implementation that usually is very common. Okay. So with that representation, we can very compactly represent an arborescence. We have the parent of each node, and then what is a correct, let's say, arborescence? Well, basically for every node we have a parent, but we have no loops, no cycles, right? Sorry, loops is usually like this to the node.
If we have no cycles other than this cycle, right? Basically in the root, right? Or if the root is undefined, if every path, like from every node, I, parent of I, parent of I, like if I start traveling the parents, I have to get to the root, right? If I don't ever get to the root, it will continue forever without arriving at the root, then it has to repeat, and so it arrives at a cycle. Right? And of course, a cycle is not that big, so it is clear. So this is an equivalent definition, which is useful in implementation, and like I think it is the one we might want in many implementations. Okay,
so that's actually enough. That's the most important part. It's not only necessary, that is basically enough. Choose parents without cycles. That is a correct algorithm. Of course, with a single node, either if it was designated as such or arbitrary, but one and only one is removed, and if the exception, if that one has no parent, or it is the one and only cycle which is any of those is equivalent.
okay, so with this in mind, we might choose greedy values for the
Parents, right? We might say, okay, let's check the graph. Let's check a node I. We can check which edges arrive at node I. Those can be used to get a parent, right? Edges that leave are not useful for getting a parent of node I. Those would be to get nodes such that their parent is I. But if we want to candidates for parent of I, if we want candidates for this, we need to look edges that arrive here. So each of those will have a cost, right? We can very greedily say, okay, I want a small, the minimum arborescence, let's just choose the smallest. So this will be I's parent. I don't know, X, let's set parent of I to X. We can very quickly, like in linear time, in one pass, or perhaps in one linear pass in the graph, right? All the edges, everything. We can basically compute this, and we will have candidates. And it is very intuitive and easy to see that if this basically creates an arborescence, we were extremely lucky, but it is clearly the minimum possible arborescence, right? Because for any arborescence, you need that the parent of, that each node has a parent, and well, this is the minimum cost. Additively, it's also a minimum. The detail is that if we know the root, which is fixed, then we don't do this for the root. It is the only node that will not have a parent, so we can actually, and many implementations do, we can actually, as a first step, delete any edge that arrives at the root because they are effectively useless for
right? By definition. Okay, so we do that, and
cycles will emerge, because otherwise we were extremely lucky and we finished.
right? So what will we do with a cycle? That would be like the
main question now. Okay, we build greedily some. This is like the key idea. Greedily choose the best value, and that's it. Okay, but it will produce cycles. What a pity. Okay, how do we solve it? This is like the core idea of how to continue with the algorithm. If we can fix this, we can fix the grid. If not, we will use something else. Luckily, it can be fixed. Okay. So this one has this parent as best parent and such, and a cycle emerges. Okay. So, what would be like the minimal way to break this cycle? Because we cannot have cycles, so we cannot have all of these edges at the same time.
Remove the biggest edge.
We can remove the biggest edge. Yes. So
let's say this is the biggest edge, right? Or the other one less than 10 or whatever. We could say, okay, remove the biggest edge and repeat. That one, I won't go into details for questions of time. That is a reasonable guess. We would like to try and see if that works. We can find examples where just doing that carelessly does not work, it's not enough. So it won't, doing that and that's it will not work. But it is a first step towards the solution because, okay, a little less greedily is we should remove one of these edges, right? But I mean one and only one. That is also something that we would like to prove, like it's not necessarily true. Perhaps the optimal solution, okay, this cycle we cannot use all of them. So at least one we need to remove. But perhaps it could be optimal to remove these two or these three edges because globally, I mean locally, yes, they are the best option. But maybe globally there are some reasons why we would not want to use neither of these three. In principle, right, of course, unless we prove it, if this can happen, right? So, just removing the largest one and saying this I can do, fails. But we can be less greedy and say, okay, maybe there are still some greedy structure to this, and it is correct to say, I will remove one and only one, and all the others stay, right? Well, that would be a guess at this point, but it is a correct guess, right? Actually, there might be an optimal solution that has this shape, but if there is, we can massage it, change it, and we arrive at an optimal solution where one and only one edge in the cycle is missing from the arborescence. Like all of the optimal parents of this cycle, I am concentrating on one specific cycle at a time right now. Right? Like I fixed one cycle. And I can start making swaps and changes such that this cycle is used almost completely in the final optimal arborescence. But only one edge will be missing. Actually, that has a nice proof by drawing. Like it's not a very common way of thinking the replacement. The idea is, okay, let's imagine my auxiliary drawing where I have the one final optimal arborescence, right? And let's say my cycle has more than one missing edge, right? It will always have at least one. But let's say that there is more than one. Okay. What has to happen so that I cannot do an exchange on the positive? When can I do an exchange and put this edge, right? So that I have more of the edges in the cycle in my arborescence, right? This is not the algorithm. This is like the proof that I can use the property that if I fix a cycle, I will only remove one, but all the others will stay, right? That is what I want to do. So if I am removing more than one, well, I can do swaps. Why? Let's say this edge is in the arboricity, so this is edge E. Sorry, this one is not in the arboricity, so it can be basically anywhere, right? It will go from some node to another one, which can be above, below, basically anywhere. This is the edge E. But then, it cannot go to the root, right? Because we have removed all of the edges going to the root at the first step, right? You can later mention small details if there is no fixed root, but let's assume there is a fixed root. So if at the first term we remove anything going to the root will never be involved in a cycle, so that's easy. Okay. Every node at which we arrive has some parent in the arborescence, right? Some other edge, I don't know, picture, right? This one is the one that actually is in the arborescence. It cannot be part of the cycle, right? Because the cycle has only one arriving here, and it's the one that I am analyzing here, right? So it is another one that is in the arborescence. Well, because of the greedy choice, if I swap this, I do not. It's better, right? This one is less expensive or equal than this one. Right? So I would like to swap. In this drawing, I can see that swapping works. If I remove this one, instead put this one, I mean, yeah, this changed the drawing if I want to be tidy, but it works. It's still an arborescence, right? So when will it not work, right? We have to think what would need to happen if in this drawing we are from one node, I draw an edge to another one and cut the path. That would be the operation. When will that fail? Basically, when will that create a cycle? That is the only thing that can fail. Well, if this is the DFS3, right? Yes, if it's a descendant, basically. Yes, correct. The edge has to go right to a descendant anywhere in the subtree. That is the only way. If it goes outside of the subtree, actually, when this drawing, we can see that, okay, we cut the edge to the parent, but if the edge goes anywhere, the one we want to add, if it goes anywhere other than a descendant, it's the other way, right? I should have cut, sorry, like that, so this edge actually arrives at this node, right? That's why I'm cutting the parent. I want to add an edge, so I have to cut the one I want to add arrives. So if I'm cutting this in the drawing, it's no more. This one had arrived. And if this one came from outside the subtree, everything works, right? So yeah, if this one that I want to add and use instead of the, sorry, this one is E. Okay, this is the one I will be adding, this one will be E. This is the only case, right? Basically, so that a cycle forms and is not connected anymore and the arborescence fail. We can see that for it to be the case, the one in the cycle has to go up, right? But that means that looking at the arborescence, right, the hypothetical optimal arborescence I am looking, if I walk along the whole cycle, I either use an arborescence edge, I mean, if I suppose that they cannot improve anymore, right? So all of these dashed edges have this structure, otherwise I can improve, right? And do a swap and get one more edge used in the arborescence. In the situation where I cannot use more edges of the cycle without improving, if I walk along the whole cycle, every time I do a movement, I either go one step down, because it will be an arborescence edge, or I jump to an ancestor, right? So I do a cycle where I can only jump to ancestor or go down. And that means that all of them, if this edge is not in the cycle, like this, then at some point you are jumping in your cyclic walk through the cycle, you are jumping above, right? And you will have to go back to that node at some point. But the only way to go down in this process, because the dashed ones go up and the ones that are in the arborescence go down, is to walk through arborescence edges going down, right? And all of those must be in the cycle. So at some point I jump, but then all of the other ones that go down from this back edge have to be in the cycle. Otherwise it will be impossible to go back, but have to go back because the cycle exists. So basically this is the drawing, and in this case, that must be the one and only one that is missing, because explicitly this is telling me all of the others are there, right? So in the situation when you cannot add anymore, only one is missing, right? You can just trust me on this and ignore the proof, but this is the full proof. We have just done the proof, right? Okay. If this idea more or less understood. Now, if you notice this or conjecture this, I mean, we have just proved, but maybe you just believe it as true. This is a useful property, right? In this case, it allows us to use a general technique. I would say a very general and very fundamental technique. So this means this is important, which I would just state as a simple principle, which is replace. Let's say many, they are usually many. Replace many, replace many things
I am trying to be very simple. Replace many things by simpler equivalent things. I'm sure you must have used this pattern of solving, of thinking, of doing algorithms at some point. It's very extremely general. But I want you to explicitly think of this like as a useful technique that you can apply many times, even when it doesn't look like it. And this would be an example. Because we have few options, we have potentially a large cycle that we have found, but now we know that we have few options of what to do with the cycle. Like inside the cycle, for example, let's make it smaller. Let's say it's only 4 nodes. Well, we either use it like this in the arborescence, or we use it like this in the arborescence, or we use it like this. I mean, this one was not used, this one was not used, and so on. 4 options. I only have to choose which one I am not using, but I will use the other 3 in this case, right? So for a cycle of length L, I have L options, right? Like usually it might have been exponential, which ones to use, which ones to not use, but now I have very few options. That might be a telltale sign that we can do some kind of simplification, right? For example, you know the strongly connected components algorithms, perhaps, or even the basic connected components algorithm. Both of those can be seen as examples of the general pattern where we can, if we only care about connectivity, or even the connectivity, or 2-path connectivity, or things like that, we can say, oh, I found 2 paths between these nodes. So for all connectivity purposes, they are the same. So I can replace them by a single equivalent simple element that ignores the details of all the traveling. Right? And the same if you have a big cycle in those problems of connectivity. Say, okay, these nodes all can reach all among them. So all the internal details of that graph are no longer important. They can contract. Okay? That is an example of this general pattern. And we can apply it here. It's more subtle. It's a more subtle replacement than in those examples where you just contract very explicitly. But it's almost like that. We will still basically contract this to a single node that works in an equivalent way. We have to be careful of what happens to the edges and the weights, right? But we can think about it. And it all stems from this property that we know that one of these edges will be missing, but all of the others will be there. And that is useful, right? Because let's say that it is like this, right? This is the one and only one node in this cycle that we select as, okay, this one does not have a parent in the cycle. All of the others have a parent in the cycle. So this is the only node that has a missing parent, let's say. That sounds so sad. This one is the one that we need help from the outside, basically, so that all of them have some parent. And all the others will be solved. If we had chosen to remove this edge, okay, this one would be. So we have like that degree of freedom still, but that's it. It's like, okay, one of these nodes will need an edge and only one edge. That is a property that normal nodes have. So that might be a sign that, okay, this works like a single node. Because a normal single node needs one edge to be complete. This full cycle works in a complicated way, but one outlet edge can fulfill it. Right? So that is the
We need to
exchange. No issue. So any ideas on how to do the replacement? Test. Any idea? I already said we replace all of this and contract it to one and only one node. And I have to remove it.
Another one, and the cost is minus the cost of the
basically something like that. Just everybody see it. Basically, we consider all edges, edges in the graph that do not touch this cycle are not affected. Edges that enter this cycle, like this one, or this one, anywhere. And for every edge that enters the cycle, okay, if I want to use this edge in the arborescence, this node cannot have two parents. So this edge being used forces this edge to be removed. So it forces our choice. And the same for any other edge that we choose to add, right? If I happen to choose to use this incoming edge, well, this forces the choice to be that I will remove this edge and only this edge. That's the only way it can work. You see? So, since incoming edges now fix and solve and also it collapses, it's like a quantum collapse. This thing is in a superposition of all the possibilities. But when you put the edge into it, it collapses and now it becomes one and only one possibility. So when it collapses, this edge will be used, but the other one will be subtracted. So yes, we can adapt the weights. And let's say this one here, let's not call both. Let's say this one has weight W and this one has weight W2. So to this one we have to subtract, basically. Well, not here, but in the modified version, we will have incoming edges as before, but incoming edges will have a subtractive factor of the edge that, like we imagine that we have already used the whole cycle, and later we will remove the one that needs to be removed, right? So to a global variable, for example, we could already add the full cycle, right? To keep the cost and not forget that it is here, that cost. We have the same problem, right? Test. Maybe? Maybe not. Thank you. Okay. So this one is subtracted. That is what we were saying. We were just saying that for each incoming edge, we subtract the cost of the one that will be removed, because that it will be the net effect when we use that edge. And the same for each one, like if this one has, I don't know, T1 and T2, using this edge forces us to remove this one, so the final net equivalent behavior weight of this edge is T1 minus T2, because selecting it will actually cause this one to be added, but this one to be removed, so this is the net effect. And now this behaves exactly like the cycle should behave. It needs exactly one incoming edge, and for each incoming edge, if we use it, the cost models what the cost will be in the actual run. Do you see it? So this is an example of this pattern. We have replaced many things, in this case the nodes in a cycle, which is more than one, by simpler equivalent things. Well, one single node. That is simple for sure. And it won't change the answer. We have to add the whole cycle somewhere, not forget that it is there, but we can add to a global node. Okay. And if we keep repeating this, we will have a full algorithm, because we have reduced the problem, right? We really choose all of the parents. If there is a cycle, we do contraction and adjust, and we keep doing this until there is no cycle. When there is no cycle, well, either we were not able to build an arborescence, and then there is no arborescence. That could happen if we have not enough edges, right? But if not, we will arrive at the end at a correct in this algorithm, it will manifest as a step where I need a parent for a node, but that node has in degree 0, right? Even if originally we had in degree 0 at every node, I think that, yeah, that is not enough to guarantee that there is connection. After some contractions, maybe we have a node without incoming edges, and that blocks the other. We could check it separately, but this algorithm should also check for
So that will work. What is the complexity of this algorithm? Sorry? Oh, that's super optimistic. M log n, like this. This can be implemented in this complexity, but it's quite non-trivial. Okay. What would be the simplest implementation you can think of? Like, I would say it is like to actually directly do this simulation, let's say, okay. I iterate through all the edges, select the minimum one for each node. So that takes the parents. I now check that and see if I find a cycle. And if I find a cycle, I go through the whole cycle, contract it actually, and then I check all the edges again to adjust the weights. So it will be something proportional to the edges at every step. How many steps do I need? Well, in general, n steps at most. So n times n. Okay, well, at this polynomial, we have achieved polynomial type. So this, I think it's quite reasonable to code. This one actually can be done, and it is good that you mentioned, yes, this is the correct complexity I have in mind. This can be achieved using structures that we have seen today. Well, that's a hint, like that is why we saw all of those structures. But I think you need to be very careful with the data structures to be able to actually. The idea is the same now. It's basically to efficiently run this process, and it is useful for the efficiency part of it, so that you don't process edges more than once. To go basically like edge by edge, so not choose for each node in the graph the best and then check for cycles, but choose any node. Initially, all of the nodes have in degree 0. So choose any within degree 0, choose the best incoming edge, and that will create something, and if there are no cycles, keep going. But at some point, that this will be like components, and at some point, cycles will be created. Like, I don't know, I have this root, and it will go like here, oh, this is a cycle. And then efficiently do the contraction, and keep going. Right? This can be done, but it is, you have to be careful. Right?
There's only log n steps, because at each step you merge to, like, at each step the number of nodes.
But you add,
Yeah, but the cycle has to be at least then 2, and now it's then 1, so it reduces to 1.
but new cycles are conformed into the contraction.
Yeah, but like, we had some number of cycles.
It is not clear at all to me that that anything is divided by 2 here. It might be the case, but to me, like if it is a complete graph or something similar to that, and you choose a triangle every step, for sure that is n steps, and that could happen. I mean, maybe there is some very clever optimization that guarantees it, but I'm not sure
Let's say
how.
we have a partition of cycles of names, more than 1, and now we have.
Oh, like contracting all at the same time?
Yeah.
You have to be careful with all the edges going through the different cycles, right? Which are quadratic number of edges. So that seems dangerous. I'm not sure if it's easy. Like if you have like a lot of triangles, then the complete graph again, and a lot of triangles. And you have almost all of the edges going from triangle to triangle. To me, it's not clear how to easily handle it. Maybe it's not that easy. Yeah, that might lead to a Boruca-like version that works in this complexity.
Yeah, but my confusion arises is actually because I assume that it's a partition of cycles and cycles. Like you may have a cycle and there's 3.
Right, that for sure. Yeah. Yeah, that's a good point. That will break that idea. Actually, this drawing is something like that. I mean, well, it's only one cycle, but this is showing that interesting things can happen. Might be a very good heuristic, like hard to break algorithm that works very fast. Like in general, there should be a lot of vision. So to recap, we do know how to do this polynomially. I guess I can give you as an exercise that you can think how to achieve it in this complexity, but this would be like the general idea. Do it incrementally. What do you need to do at every step? Select any of the nodes that has 0 incoming edges, and well, choose the best incoming edges and add it. If it doesn't create a cycle, that's awesome. If it does create a cycle still, then you have to do the contraction. When you do the contraction, that's where you meldable heaps are useful. Like, it is useful to store the incoming edges to each node in a heap, so you can choose the minimum one. And when you contract, all of those get fused together. Actually, they get fused, but before the fusion, the cost gets modified. So you also need to be able to add a constant to all of the heap. But that can be done. I think you can figure it out. There are very standard things like helper variable and such to do that, but you have to be careful with that. And also, you probably need 2 independent addition set unions, like union file structure. One to have the final IDs of the merging cycles, right? And a separate one for the weak connectivity, which helps you detect if it's created a cycle or not. So you probably need 2 independent union files plus the meldable heaps. But like all of that works in log time, so it's not log square, it's log n. Even it can be done in log square with some of the other more competitive programming traditional structure, like probably some small thing. Right? I actually think this pattern happened like last year or the previous one. I don't remember if the regional or a championship at some Latin American contest. There was a situation like, okay, yeah, the expecting one is log square anyway, but it's subject to this heap thing that, okay, if you use the correct heap, you remove one log. Right? But I think it wasn't necessary, but you might have that in a big notebook, and okay, it's now faster. Right? So always good to have margin of error to be more inefficient in other places of the code so that you can squeeze. Okay, any questions? So, apart from this specific algorithm, which is very interesting, although it doesn't appear very often, but there are problems where this idea is useful. It can also be useful as an idea to thinking. Like maybe you have a problem where you can model it as an arborescence and you do not want to or cannot use the full algorithm, but the idea of the full algorithm helps you. The same thing happens with flow very often. Like, okay, this would be a flow in this huge graph. How can I model that same idea but very fast? This can happen sometimes. Like, okay, this problem would be like running this algorithm in this very particular situation. How can I simulate it fast? And also, I think this idea is very general and very useful and easy like to forget because it's tricky. It's like you have to. It's a constructive idea in a way. You have to invent the equivalent thing. But I think there are like tips. When you notice that a larger structure has like something in common with the single element, that is like a telltale. I might do replacement. Here is once you get to the conjecture or the proof that, okay, I can use all except one. And if I use all except one, then this whole thing has like one free space. And that is the property of the single node, right? And so that might lead to the idea of I should contract. Okay. Okay, I think we should stop for today. Go to see you at lunch.